So we were looking at problems like this. We might have had the integral of the square root of 16x squared plus 9 over x to the 4th dx. What tells us when we look at that integral that that integral is probably a trig substitution problem? You've got a square root, and inside you have an x squared. That's your big indication that that's a trig substitution problem. All right, so we had 3 different rules for which substitution to make. In this case, we have something squared plus something squared. When we had squared plus squared, our substitution was tangent. All right, so x is going to be all right, except you got to be careful. If I were to let x equal 3 tangent theta, when I plug in here, I'm going to end up with 16 times 9 tangent squared plus 9. That's not quite going to work. I need to make it so I get 9 tangent squared plus 9 so that I can factor the 9 out. So in other words, when we did these problems yesterday, we didn't have any number in front there. How about if I simply divide this by 4? Because then when I plug in, when I take 3/4 and I square it, I'm going to get 9/16. And the 16 on bottom will reduce with that 16 on top. So if you don't have a number there, then it's just going to be a tangent theta. If you have a number in front, then you want to divide by the square root of that number so that when you square, that number will reduce out. Okay, so what we did next is we came over here and we simplified this thing. So this square root is now going to be 16 times 9/16 tangent squared theta plus 9. These 16s reduce out nicely. We can factor out a 9, and we're left with tangent squared theta plus 1. And the whole idea was the square root of 9 is a nice number. It's the number 3. What happens with the tangent squared plus 1?
So that for secant squared?
Tangent squared plus 1 becomes secant squared. And then the square root of secant squared is simply secant. So this whole big ugly square root thing is all going to simplify down to simply be 3 secant theta. What are we going to do about this x to the 4th here?
So then 3/4 tan.
So I've been the 3/4 tan theta. And what are we going to do about that dx right there? Take the derivative. So dx is 3/4. What's the derivative of tangent? Secant squared theta d theta. So there's all of our substitutions. This ugly square root thing, that's going to be 3 secant theta. X to the 4th, we'll plug in 3/4 tangent theta. And dx, we will plug in 3/4 secant squared theta d theta. So we end up with the integral of 3 secant theta. I said secant and I wrote sine. Divided by, down on bottom, I got to take 3/4 to the 4th. 3 to the 4th is 81. And 4 to the 4th is 256. Sounds right, because it's 16 squared. And then that's going to be tangent to the 4th theta. And then finally dx is going to be 3/4 secant squared theta d theta. All right, so because we had this 16 here, that caused us to write a fraction there, which is, of course, going to cause us to have fractions in our answer. We'll deal with that. Not so bad. All right, so I'm going to write this as, I'm going to have the 3/4. I'm going to flip and multiply here, so I'm going to have 256 over 81. I'll reduce that fraction in just a minute. And then inside my integral left over, I have secant cubed divided by tangent to the 4th. So you're saying I forgot that 3 right there. I absolutely, positively agree. There it is right there. Absolutely. I lost a 3. Thank you. Never mind?
Yeah.
Good? You sure? All right. How do you integrate that? Change it to sine and cosine, because when you have secants and tangents, you need secant to have an even power, or you need tangent to have a odd power, and neither of those happen in this problem. So this is one where you're going to have to change everything to sines and cosines. All right, so 3 times 3 is 9. 9 over 81, that's a 9 on bottom. And then 256 divided by 4? 64. Integral of secant cubed is 1 over cosine cubed. Divided by tangent to the 4th is sine to the 4th over cosine to the 4th. So that's 64/9. Flip and multiply. Cosine over sine to the 4th. Can we integrate that? U equals sine, because the derivative of sine will give us cosine. U equals sine theta. Du is cosine theta d theta. Works out perfectly. So this becomes 64 over 9, the integral of 1 over u to the 4 du. That's 64 over 9 times, what's the antiderivative of 1 over u to the 4th? U to the negative 3 over negative 3 plus c. Almost done now. Our problem started with x's way back up here. You can't even see it anymore. It's taken so long. We started with x's. So when we get all done, we should end with x's. All right, so this is negative 64 over 27 times u with sine to the negative 3 theta plus c. And then we need to solve for theta. And the way we did that is we went back to our original problem. So I'm going to rewrite that. X equals 3/4 tangent theta. I'm going to rewrite that as tangent theta equals 4x over 3. And draw myself a little triangle. Here's my angle theta. Tangent is opposite over adjacent. So I go talk to Pythagoras. How long is the hypotenuse? Square root of 16x squared plus 9. And notice once again, we mentioned this yesterday. Our original problem, the original thing that we really wanted to get rid of was the square root. That square root always comes back to haunt you in the end. always shows up right there. All right, so final answer now. Negative 64 over 27 times sine. Sine is opposite over hypotenuse. So that's going to be 4x divided by the square root of 16x squared plus 9. All of that raised to the negative 3 plus c. Questions on that one?
We didn't determine this with definite.
Wonderful question. Yes, absolutely. This question was, how about definite integrals? Will we do that? Sure we will. How about the integral from 0 to the square root of 3 over 2 of t squared divided by 1 minus t squared to the 3 halves dt. All right, once again, looking at that, you should look at that problem and you should say, hey, I think I should use trig substitution. What tells me that I think I should use trig substitution? Well, first off, I see I have a square, and then I have this power of 3 halves. But what can you tell me about a power of 3 halves? Other way around. The 2 is your square root, and the 3 is your power. So there really is a square root there. It's just not written the way we're used to seeing it. So a 3 halves power means you have a square root and then you cube it. So we do see that we have our square and we have our square root. That's a strong indication of trig substitution. This time we're in the form of a squared minus t squared. So this time our substitution is t equals what was it when you had a squared minus x squared?
Sine.
That was sine. T equals sine of theta.
Just because one is A, right?
And a happens to be 1. If this were a 9 here, then it would be 3 sine theta. Correct. Okay, so well that's pretty handy because that means when I go to plug it in, dt is just going to be cosine theta d theta. And finally, 1 minus t squared to the 3 halves is going to be 1 minus sine squared theta to the 3 halves. What's 1 minus sine squared? Cosine squared. So that's going to be cosine squared to the 3 halves. How much is cosine squared raised to the 3 halves? Cosine cubed. Because you have a power followed by another power, you multiply your powers. Or this is a square, and this 2 on bottom of this fraction is a square root. What do squares and square roots do to each other? They cancel. So this is just cosine cubed theta. Okay, so we're going to have the integral. T squared. T squared is going to be sine squared theta. Divided by that ugly thing on bottom we discovered was cosine cubed theta. And then dt was cosine theta d theta. Now we're going to fiddle with the numbers. So remember that this is a t number, 0. So I have 0 equals sine of theta. So if 0 equals sine of theta, what does theta have to be? 0, because sine of 0 is 0. And conversely, for the top number, I have square root of 3 over 2. Square root of 3 over 2 equals sine theta. What angle for theta gives me sine to be square root of 3 over 2? It's one of the 30, 60, 90 triangles. Which one? 60, except we don't work in degrees in this class. Pi over 3. So you change your numbers just like you change your numbers when you do U substitution. Really nothing different there.
So you plug the t in?
These are t numbers, right?
Okay.
So I plugged t in, so I had square root of 3 over 2 equals sine theta. And then I had to look at that chart that I've memorized and remember that the sine of pi over 3 gives me square root of 3 over 2.
All right.
Okay? So you change your numbers just like you do with U substitution. Really nothing different there. All right, well, this works out fairly decent because this becomes the integral from 0 to pi over 3 of tangent squared theta d theta. All right, because we reduced one of the cosines, we got sine squared over cosine squared. What's the antiderivative of tangent squared theta d theta?
Tan theta minus theta.
Tan theta minus theta. And how'd you get that?
Looked at my handy dandy note card.
Looked at my handy dandy note card. All right. What if this one didn't happen to be written on your handy dandy note card?
That's as far as I go.
Well, this goes back to section 8.3. Usually we want secant to be even and we want tangent to be odd. Crap, tangent is even. What do? If we go to sine and cosine, we're right back to where we were. That doesn't really help because we have sine squared over cosine squared. We could let u be cosine, but then I'm not going to get the sine squared on top.
Can you write tangent squared as 1 minus secant squared?
You use the Pythagorean identity. That's correct. So how'd that work again? I know that sine squared plus cosine squared equals 1. So tangent squared is, what was that identity? Cosine squared plus sine squared equals 1. If I divide everything by cosine squared, I get 1 plus tangent squared equals secant squared. So tangent squared is secant squared minus 1. So this becomes the integral from 0 to pi over 3 of secant squared theta minus 1 d theta. And that's very helpful because I know the antiderivative of secant squared. The antiderivative of secant squared is tangent, so that's tangent theta, minus the integral of 1, theta, 0 to pi over 3. Now, I'm seeing on quizzes and homeworks and things still, there are some people who are absolutely insisting on, at this point, plugging the t's back in. You don't plug the t's back in. This is the whole reason for changing the numbers. When you get to this point, all you got to do is plug the numbers back in. So, this is tangent of pi over 3 minus pi over 3 minus tangent of 0 minus 0. I go to my big chart in the sky that I've memorized. Tangent of pi over 3 happens to be square root of 3 minus pi over 3. Tangent of 0 happens to be not 1, 0, and 0 is 0, so that's it. Let's subtract 0 and multiply. Questions on that one?
So it's probably going to be nicer when it's definite.
It's almost easier when it's definite because you don't have to draw your little triangle and figure things out and plug your x's back in. Well, in this case, plug your t's back in. It's almost easier when it's definite. Yes, I agree. Other questions? All right, let's try another definite one then. Oh, let's see if I can just make one up. How about the integral of x divided by the square root of 9 minus x squared dx. And we're going to go from, let's go from 0 to a half. I think will work. What do I do?
U sub.
Do what?
U sub.
U sub? What do you mean U sub?
You can do U sub on this one.
Ah, you're too quick for me. You weren't supposed to figure that out that fast. Just because you see a square root in something squared, it doesn't always mean you have to use trig sub. Why can you do U sub on this one?
Do the X on top.
If U is 9 minus x squared, du is going to give you a 2x. You're going to get that x on top. Look for that. Every now and then, your author likes to sneak one of those into the homework. Can you do this one by trig sub?
Yeah.
Absolutely. Is it hard? Absolutely. Would you rather do U sub?
Yeah.
You're darn right. Watch for that. Every now and then, your author and your teacher likes to sneak in such a problem to see if you're paying attention. This is really a U sub problem. You do not need a trig sub. Trig sub will work, but if you can avoid trig sub, that should be your goal. So I need to sneak a -2 in there, which means I need a -1/2. So this is going to become -1/2 integral. I'll figure my numbers out in a minute here. Square root, not a big square root. That'll work. 1 over u du. That works because the square root of 1 is 1. That's not really how I meant to write it, but it still works. And then what are my numbers? My numbers are, when I plug 0 in, I get 9. And when I plug a half in, I get 9 minus a quarter. It's 9 minus a quarter. 8 3/4. That is correct. I would have preferred you to give me the improper fraction, but I'll accept 8 3/4. How many? What's the other one? Well, you take 8 times 4. What's 8 times 4? 32, and then you add 3, so it's 35 over 4. 35 over 4. All right, so we have the -1/2. We integrate. What's the integral of 1 over the square root of u? 2u to the 1/2. And then we got to plug in our numbers. We plug in, what did you say that was? 35 over 4? Those reduce out. That's nice. So we have negative square root of 35 over 4 minus, but then we got another negative, so that's going to be a plus square root of 9. 3 minus the square root of 35 over 2 is, I think, how I would write my answer.
See, I flipped and got rid of the negative.
What's that?
I flipped and got rid of the negative.
Yeah, that's fine. What he's saying is he noticed that the bigger number was on bottom and top, so he flipped his numbers, which got rid of that negative sign there. And you should have gotten exactly the same answer. Yeah, that's fine. All right, moral of the story is look for U substitution. This is a problem that you can do by U substitution in about a minute. You can do it by trig substitution in about 10 minutes. U substitution is better. Absolutely. Questions on that one?
So we basically just look for like log x.
Yeah. Look
Or
for,
x,
if I let u be the thing underneath the square root, do I get the thing that's left here? And that works out nicely in that case. All right, here's another problem that I like a lot. The integral from -2 to 2 of the square root of 4 minus x squared dx. Can you do that? Can you do that problem by U substitution? No, U substitution does not work, because if you let u be 4 minus x squared, du is a minus 2x dx. I don't have an x out here to balance it with. U substitution will not work. So what do you do?
Looks like sign.
Looks like sine, I agree. Can anybody give me the answer without doing trig substitution? 0 is not the right answer. Good guess, though. The correct answer is that. The big question is, how did I do it?
Shortcut for less shots.
Oh, that's a 2, not a 4, by the way. No, it's not a shortcut that I'm about to show you. It's a shortcut you already learned. If you graph this function, what's it look like? It's half a circle. It's the top half. So if you remember your Calc 1, integrals are areas. I've given you half a circle. So how do you find the area of a circle? Pi times the radius squared. But we only have half a circle, so I had to divide it by 2. All right. So again, that's another problem I love to put on a test. Just to, again, to see if people are remembering that, hey, in Calc 1 we learned that integrals are areas. That's really just half a circle. I don't have to do trig substitution.
Pi times radius squared.
Pi times radius squared, except then you have to divide by 2 because it's only the top half of the circle. All right, so watch out for problems where you can do U substitution. Watch out for problems where you can make the area argument and get the answer without doing any work.
How would you write a quarter of a circle?
If the integral went from 0 to 2.
Oh, okay.
If it went from 0 to 2, then I'd only have that part. I'd only have a quarter of the circle. And then instead of dividing by 2, I would divide by 4.
That you did this for pretty much because, right, any chunk of the circle, because that looks basically like the radian arc.
Yeah, you could do it for any chunk of a circle. Yeah. Work. All right, so that's trig substitution. We move on to section 8.5. We'll spend a couple of days in 8.5. This is called partial fractions. Well, partial fractions, it should be no surprise to you that these are going to be integrals that involve fractions. So we might have the integral of 1 over x squared minus 9. We can already answer this question. How? Without knowing anything about partial fractions, we can answer this question.
U substitution.
U substitution, unfortunately, would not work.
You're right.
Because I would let u be the bottom. When I take the derivative, I would need a 2x. I don't have an x up on top to balance it with.
Is it, I'm kind of guessing, hyperbolic tangent?
Close.
Hyperbolic substitute.
Inverse hyperbolic tangent. This fits into our inverse hyperbolic tangent form. Should go back and look that up. And when we wrote our inverse hyperbolic tangent form, we ended up with answers that involved logarithms. But we can do this another way. And the technique that we're going to use is called partial fractions. Here's what we're going to do. We're going to notice that the denominator factors. Correct? You can factor the bottom as x plus 3x minus 3. That's your big hint as to when will we use partial fractions. You'll use partial fractions when you have a fraction and the bottom factors. That's your big clue right there that this is partial fractions. What do you do if the bottom doesn't factor? You complete the square, and then you've got to use the inverse trig functions that we used before. Okay? Bottom factors. Now, what we're going to do is we're going to do some algebra. And the algebra is called partial fraction decomposition. Sounds fancy. What it means is we're going to break this fraction into two fractions. And it's called partial fractions because we're taking part of the denominator for this first fraction and part of the denominator for that second fraction. The whole question is, what numbers do we need for A and B to make this work?
You have to multiply together to be one, so.
No, they don't have to multiply together to be 1, because think of what you would have to do to add these two fractions. What would you have to do? You have to get a common denominator. So you're going to have to multiply this one by x minus 3, you're going to have to multiply this one by x plus 3, and then when you add all that up, it has to equal 1. So in just a minute here, we'll figure out how do you do all that work. My question is, would this help? If I could take this integral and write it this way, can I integrate a number divided by x plus 3? If I knew the number, let's say the number was 4. I don't know if 4 is the right number or not.
Yes.
How would you integrate 4 over x plus 3?
U sub.
U sub. U would be
X plus 3.
x plus 3, and you're going to end up with an ln of x plus 3 when you get all done. The same with this one. U is going to end up being x minus 3. We can integrate, we get an ln. So that's the idea. We can take something that starts with a quadratic on bottom, we factor it, we get linears. When we get linears on bottom, we can integrate by doing U sub. Now, the hard question is, what's the number for A and what's the number for B? Here's what you do. You take this equation and you clear the fractions. So I'm going to take that equation, I'm going to multiply everything by x plus 3 times x minus 3. What happens on the left-hand side when I take 1 over x plus 3 times x minus 3 and multiply it by x plus 3 times x minus 3? I get 1. Equals. What happens here? The x plus 3's reduce out, I get a times x minus 3. Plus, what happens with this one? The x minus 3's reduce out, and I'm left with b times x plus 3. Alright, then I'm just going to do a little bit of arithmetic here. This is 1 equals ax minus 3x, or I'm sorry, minus 3a, plus bx plus 3b. Right, so all I did is I took the a and I distributed it through, and I took the b and distributed it through. We do a process now called equate the coefficients. And what that means is, if I look at everything that has an x on the right-hand side, that has to add up to all the x's I have on the left-hand side. I don't have any x's on the left-hand side. So that tells me that ax plus bx has to add up to 0 because there's no x's over there. I'm going to take that equation and I'm going to divide everything by x, and I get a plus b equals 0. The other thing that has to happen is all the numbers on the right-hand side have to add up to all the numbers on the left-hand side. The numbers on the right-hand side are negative 3a plus 3b. That has to add up to the numbers on the left-hand side. The numbers on the left-hand side are 1. So notice what I end up with. I end up with a system of equations, 2 equations, 2 variables. How do you solve 2 equations, 2 variables? One way to do it is using a matrix. That's correct. I think that's overkill for this problem, but you could do it that way.
Solve for one, plug it in.
Another way is to solve for one, plug it into the other. For example, a equals negative b. And I take that and I plug it into the other one. A equals negative b. So I'm going to have negative 3 times negative b plus 3b equals 1. Well, that's 6b equals 1, which means b is 1/6. And then I take that and plug it in back there, which says A is negative 1/6. All right, so I want you to notice the typical calculus problem again. So far, all of this, there's absolutely no calculus in there. All I've done is algebra. I did all that algebra to come back up here and say I can write this integral as the integral of A turned out to be negative 1/6 over x plus 3, and B was 1/6 over x plus 3 dx. And now I can integrate. Oops, I'm sorry, the second one was x minus 3. That's going to be negative 1/6. What's the integral of 1 over x plus 3? ln of x plus 3. Plus 1/6 ln of x minus 3 plus c. The only calculus in this whole problem is going from here to there, integrating. Everything else, piles and piles of algebra.
Does it matter if you like leave it in terms of like A and B and then solve it? So you get like A ln of x plus 3 plus B ln of x minus 3 and just plug it into the end?
Sure, that would be fine.
Same thing.
Yep. Questions? Oh, somebody asked the right question.
How'd you get the x plus b equals 0 again?
I took all the things that had an x on this side and I added them together, so ax plus bx. That had to equal all the things that have an x over here on this side. But there aren't any x's over there, are there? So it just has to be 0.
What if there was?
What if there was an x over there?
And you just said,
It'd be okay. We'd say if there were a 3x here, then we'd have a plus b equals 3. It'd be okay. All right, the right question is that nobody's asking, is there a shortcut? And the answer is yes, there's a shortcut. So let me show you the shortcut.
Well, hopefully you wouldn't set us up for that. Say now, you're kidding.
There is a shortcut. All right, so let's say we had integral. Let's put an x up here this time. 2x plus 4 divided by, I need something on bottom that's going to factor. Let's say we have x squared minus 4x minus 12. Does that factor? That's not very good though.
you plus 4.
Let's change that to 2x plus 5 up on top. Why did I want to change that? We'll see in just a minute. All right, so what we're going to do is we're going to take 2x plus 5 divided by x squared minus 4x minus 12 equals a over something plus b over something. How does x squared minus 4x minus 12 factor?
Plus 2 minus 6.
X plus 2 and x minus 6. So the reason I wanted this to be 2x plus 5 instead of 2x plus 4, if it, what's that? Well, even better than that, if this was 2x plus 4, I could have factored a 2 out, and I would have had an x plus 2, and it would have canceled with that x plus 2. I didn't want it to cancel out on me. Okay, so we do the same thing we did last time. We cross multiply. So we're going to multiply everything by the common denominator and get rid of all the fractions. When we do that, we have 2x plus 5 equals a times x minus 6 plus b times x plus 2. Here comes the shortcut. going to pick my favorite number in the world, and I'm going to plug it in for x. Anybody got a favorite number?
0.
No. 10, no. 5, no.
13.
No. 6. 6 is my favorite number this time. Why do I like 6? Because when I plug in 6, it's going to give me 0 right there. So I'm going to plug in x equals 6. When I plug in x equals 6, on the left-hand side, I get 6 times 2 is 12, 12 plus 5 is 17, equals b times 8. And the nice thing about the number 6 is it made this one go away, which only left me with one letter, letter b. So b is 17 over 8. Now I'm going to plug in my next favorite number in the world. And this time, my next favorite number in the world is negative 2. You caught the trick already. Why do you like negative 2? It makes this one disappear. That's exactly right. So you plug in the numbers that make the terms disappear, and you simply solve. So I plug in negative 2, I get negative 4 plus 5, that's 1, equals a times negative 8, which means a is negative 1/8. Was that a little quicker? No, it was a lot quicker. So this becomes the integral. A was the number negative 1/8 over x plus 2, plus b was the number 17/8 divided by x minus 6 dx. So that's the shortcut for doing partial fraction decomposition. You don't set up a system of equations and solve the system of equations. You simply plug in the right numbers and make it work out for you. All right, so now we do some calculus. This is negative 1/8. What's the integral of 1 over x plus 2? ln absolute x plus 2 plus 17/8 ln of x minus 6 plus c.
I almost don't want to ask for there to be definite limits.
Yeah, but would it be a big deal if there were definite integrals? I mean, if I put some numbers on here, like 0 to 3.
Would you have to change the bounds?
Yeah, you don't have to.
No, you wouldn't have to because you didn't. Well, I mean, technically you did a u sub when you integrated, but you didn't bother writing the u sub down. We've seen this pattern. So all you have to do now is plug the numbers in and you'd be all done. So definite integrals aren't really a big deal here.
I was curious.
So could happen.
This class is a whole lot of shortcuts for everything in Calc 1. Like this would have made stuff in Calc 1 really easy.
Well, but you couldn't do this in Calc 1.
Really?
And the reason was in Calc 1, we didn't have that thing. So that's why you had to talk about logarithms before you can do this integration technique.
They got it down.
Got it down.
And it might not be so easy if we haven't already had like a semester and a half dealing with integrals,
Correct.
derivatives.
Been dealing with integrals and derivatives a lot. Now, I will warn you, Friday we'll do more of these problems, and they do get harder. Anybody have a thought of how these could get harder?
Trig.
There will be no trig, but that would make them harder. I agree there. We will not have trig.
Will there be roots?
What do you mean, will there be roots?
Factoring could get really hard.
The factoring could get ugly, that's true. The other thing that could happen is when you factor, you don't always get two linear terms. What if you had the integral of, say, 5x over x squared plus 4 times x minus 3?
Then you have x plus 2 squared on the left.
No, because x plus 2 squared is x squared plus 4x plus 4. So this x squared plus 4 doesn't factor. So there's something special you have to do when that happens, when you have a quadratic on bottom. The other problems we'll talk about are, what if the bottom factors as x plus 2 whole thing squared times x minus 3? Then we have what we call a repeated linear factor. We have x plus 2 times x plus 2 showing up twice. There's something special you have to do for those.
Is it A plus B plus C, where there's three different terms underneath them that you solve for all three this time?
Yes, for each of these, we will have an A, a B, and a C. And they look similar, but the way you set up the A and the B and the C are slightly different. And we'll see that on Friday. So if your bottom factors, where you get multiple, if you just get linear terms, partial fractions is pretty simple. It gets a bit harder when you factor and you get a quadratic on bottom or you get a repeated linear. And we'll see on Friday how you handle those. Questions?